We good on sound and video? Great. Okay. So good. Where did we leave off? I'm going to assume that basically everyone here and on the video has already watched the last session. But so what we're thinking about is this algorithm for learning multi-calibrated predictors. Okay. And we'll go through it again. One thing that came up in the break is that I'm talking about initializing. Let's go back to the highest level version. Talking about initializing this predictor P naught to be a trivial predictor. I need not do that. I can also think about pre-training a predictor, bringing that in, and even incorporating sort of level sets from that predictor into my collection. Okay, this might be a good way to build up on existing techniques. So really this boosting strategy could similarly be thought of as a post-processing procedure to turn your favorite pre-trained model into a multi-calibrated predictor. Okay, so really I can handle any arbitrary predictor here. Good. It came up that we need to think about how to check these constraints and see if they're violated, both computationally and statistically. I promise you we will get to that. And good. And we're thinking about this update and why it makes progress. Okay, here's the more technical version. Again, the truth is that whenever you're working with predictors and you need to reason about the predictions that the predictors are making, there's some circularity, there's some complication, both statistically and just sort of representationally. How do you represent these predictors? There's a lot of technical details that, or formalisms that you can use to handle it. The easiest way is just to round your predictions to the nearest interval. And you need to round them to roughly 1/alpha buckets if you want to work with alpha error. Okay, so that's what we'll think about here. Consequently, then, this condition requires us to reason about slightly smaller errors. And that will show up in the time and statistical complexity. Okay. And I promise you we can make all of these details very formal. I think for the sake of this talk, that's about the level I want to get into it. Okay. Good. So we did say, though, that if this algorithm, MC-Boost, returns something, if it returns a predictor, and basically just by the termination condition, it's guaranteed to be multi-calibrated. Okay. The question we need to ask then is, when does this predictor terminate? Okay. To argue this, we're going to show a straightforward but important lemma that the boosting algorithm can run for no more than, let's say, poly and 1/alpha iterations. Okay. From this lemma, we get an immediate corollary, which is a bound on the complexity of the predictor that we're going to output in the end. Okay. In particular, it's not hard to see that the predictor p tilde of x is eventually computed just by sort of the iterative summation of our updates. So we started with a half, could be p naught here. And then we're nudging our predictions by some eta by our c's that we identified times this indicator of the prediction at the teeth predictor. Okay, this indicator where we're leveraging PT, I leave it as an exercise to the audience, but it's actually a bit subtle to figure out how to implement this without getting, say, a quadratic blowup in the complexity. You just need to do some rewiring tricks. But the upshot is that our complexity is roughly linear in the complexity of our underlying predictors. This underlying subpopulations. Okay, so if the complexity is k to implement a function in C, then the complexity of the predictor is bounded by roughly t times k, where t is the number of iterations, and we bound it polynomially in alpha. Yes?
By complexity here, You're referring to something like threshold circuit complexity?
Yeah, sure. Threshold. I'm not going to be too formal here.
Yeah.
I'm, in fact, just like the tilde is not hiding log factors. It's just hiding like implementation details. Like if you work with a very concrete circuit class, then yeah, you need to be able to implement these equality checks or threshold checks. That's so for a sufficiently rich computational model, it's roughly in the underlying complexity of C.
Just a clarification, that's only 1 over epsilon the lemma. That doesn't depend on anything. It really just depends on alpha, right? You can give me explicit polynomial that doesn't depend on any.
That's right.
For the class. Okay.
Here it's going to be 1 over alpha to the 4th. Yep. Great. So we'll go through. And no, like Nati said, no dependence on C. Okay. Why should this be true? Okay. It's going to go by a very standard potential argument. Familiar to people if you've seen gradient descent or multiplicative weights, these kinds of algorithms, where we're going to define some potential function. Okay. In this case, it will be the expected squared error of your predictor. Okay. Because it's a squared error, it is non-negative, right? You can't have a negative value here, which means that no matter where we start from, if we remove potential, eventually we're going to hit 0, and we can't go further than that. Yeah.
Sorry, I'm just briefly blinking on in your update. How are you setting eta?
I haven't.
Okay,
Good catch.
It can be negative, right?
Yes.
Okay, great.
Yeah. Eta can be negative, and we'll talk about what it ends up being. That's a great catch. Good. So this potential function is non-negative. It starts at good. The other fact we need is like, what's the maximum value this could be? Well, you know, its maximum value is a constant, because it's an expectation of 0s and 1s. Okay, and so then the goal to argue why this potential argument, why we can't run for too many iterations, is to show that at every update, we make significant progress in this potential. Okay, the potential drops by a Paulian alpha factor. Okay. Everybody clear that if we manage to show this, then we've proved the lemma. Okay, so how does it go? Well, you know, there's going to be some just arithmetic here, but I'm going to expand out the definition of PT plus 1. Okay, where here is my updated predictor, and I'm taking the squared error. I'm going to expand that out in order to pull out this y minus pt term squared, which just gives me the potential from before to cancel that out. Okay, and I'm left with 2 other terms. The first term is exactly this condition on which we're basing our update. Okay, it's from the update condition in the algorithm. This value is at least alpha squared. Okay, and from just bounds on these values by the boundedness of C, then this value is less than or equal to 1. Okay, so in sum, we're going to be able to balance terms, choosing our eta appropriately to account for the sign, and choosing it of magnitude so that the difference here is at least, let's say, alpha to the 4. I don't mean for you to get every last detail on this slide the first time we go through it at that pace, but it's just to say that, like, it's not a complicated argument. You're just expanding squares, you're canceling terms, and then you're looking at the fact that we have a bound from the update condition. Okay, and that bound, the fact that you're only updating when you find a significant violation, is what gives you significant progress in this potential argument. What it says too, as sort of corollary or intellectual just thought, is that actually these updates are moving you closer. These updates are improving your squared error. At every update, we're improving our overall squared error. Okay. And that's it. Okay. So yeah, good. So we have a bound on the number of iterations that we'll ever make, and this bounds our complexity. And now the thing that we need to turn to is checking these multi-calibration constraints. Mika, is there a question?
There's a question online that's asking, is it possible to define NT as exponential over T for faster conversions? It might be N or T, I don't know.
What was the question about how to define it?
Is it possible to define it differently as exponential over T so that you can get faster conversions?
Not sure. Yeah.
Okay.
I don't know. So I'm doing this additive nudging update. You certainly can also implement this with a multiplicative weight update. That's the question. Yeah. Sure.
Recall David's question, why it does not depend on the complexity of C. I think it implicitly depends because you find that CT actually you need to take into the complexity into account.
This is the number of iterations. So I do need to talk about how we check these constraints, but I only need, so I'm saying how many times do we need to check the constraints effectively?
But it's just the number of iterations that we need to find that C. So that actually does not.
That's right. Yeah. So this bound is on the iteration complexity of the algorithm.
So how to find that C? But we don't ever need to consider.
Yeah, I'm about to talk about that next, of how to find the C. Yeah. Good. Yeah.
I guess the way it feels like it does depend on C, like, so let's imagine that C are all individuals, right? Then essentially, like, if my alpha is set even remotely too high, I'll make no updates at all because I don't have enough weight in any individual to make an update. And then as soon as the alpha is low enough, then I'll make updates on every individual. Right, and so in some sense, alpha is implicitly dependent on how big my C classes are.
Certainly, there are reasons to set alpha in accordance with, say, the size of the subsets that you want to protect. But once we fix alpha, then for any C, this algorithm runs with polynomial and 1 over alpha iterations.
I mean, another reason it implicitly depends on C is because the potential function, if C is very not complex, the potential function won't have time to go to 0. Like being multi-calibrated is not the same as having potential to be 0. So you'll run much less than alpha to the 4 iterations. So in that, like the upper bound does not depend on that. Yeah, no, I totally agree. So it's a good direction in which it depends on C is what I mean.
Yeah, sure. Like I think these are all true statements. I think the point is just that there is an explicit upper bound independent of C. Good. So okay, so the final thing in putting this algorithm together then is to ask, how do we check these constraints? Okay. Mm-hmm.
I think you said that implicitly, do we know that the algorithm will return a good hypothesis at the end or something like that? Or
what do you mean good?
that will have a good prediction or?
So it will be multi-calibrated and we'll talk about whether that's a good thing.
Or basically squared error. Squared error should go down.
So squared error should go down, like, yeah, all great questions. Wait for Parikshit's talk, wait for 10 minutes from now. Good. So how do we audit? The key insight here is that we can reduce this auditing problem, auditing for multi-calibration, to a certain standard machine learning problem. Okay. This is the so-called weak agnostic learning problem. Okay, where we're given data. I'm labeling it by Z now, just to indicate that it could be something as a function of Y, a function of your current predictions. And we're saying that if there exists some C in our class, such that there's significant correlation with the Z labels. Okay, there's correlation at least alpha. Then you need to return me a hypothesis that, let's say, gets at least polynomial in alpha correlation. It's a correlation detection problem, and it's a promise problem. That if there's a significant violation, find me something with slightly less significant violation. Okay. And really, truly, this problem is computationally equivalent to the auditing problem. That if I make no assumptions about Z, then I can plug in my labels from, I can plug in y minus pt as my Z. Okay. And so what this says is that really this auditing leverages exactly the same primitives that we would use for some sort of boosting algorithm. Right. This weak learning is thought about in the context of boosting a lot. Okay. And so the upshot of that is that the sample complexity, right, where have I touched the data before? The only place I touched the data is in checking these constraints, right? Evaluating this expectation, okay? And so the sample complexity needed for this weak agnostic learning problem scales with the VC dimension of C, logarithmic in the class C if it's finite, and polynomial in 1 over L. So Megan.
What happened to the conditional P of X?
Yeah, so we can it can be a Turing reduction, where we'll think about each level set separately, and run, let's say, 1 over alpha iterations of the weak agnostic learning based on just the conditional distribution. Good. So here's the summary. Here's sort of what we talked about. So the final theorem that we get is the following: fix an identifiable collection C. What do I mean by this? I want it to be computable in complexity of, say, S, some concrete complexity. And I want it to be auditable in the sense that there's a weak agnostic learner for the class C. Okay. If those things are true, then there exists a learning algorithm, namely this multi-calibration boosting, that makes polynomial in 1 over alpha calls to this weak agnostic learner, and in the end returns to you a C alpha multi-calibrated predictor of complexity scaling at roughly as C times a polynomial again in 1 over alpha.
So how is this different from just learning P star in the agnostic pack sense with respect to this class? I mean, you just did directly give me C like this. Think of C as a concept class.
Yeah.
I'm just going to learn P star.
Yeah.
And it seems that being calibrated is basically the same as up to maybe some exponent alpha is learning is the pack learning P star. And what you're doing here is essentially just saying I'm going to let pack learn P star, which I can do with finite P star.
Great. So what we'll show in a second is that for certain versions of pack-learning, let's say loss minimization, you can, what we'll show is that multi-calibration and other variants imply loss minimization, imply some sort of pack guarantee. And no, in fact, the guarantees of multi-calibration are stronger than just pack-learning, and you have to stick around for Parikshit's talk to really understand that.
Can you go back one slide? So C is mapping X to 0, 1, and then H is mapping X to -1, 1.
Uh-huh.
What's the reason for that difference here?
I'm not taking an absolute value here. I'm just sort of saying arbitrarily Z could be plus minus. Yeah. All of these things can be interchanged. Yeah. So let me push ahead. I'm going to talk about sort of so I'm going to switch gears to thinking about outcome indistinguishability. And in particular, I want to think about comparisons of multi-calibration and outcome indistinguishability to more traditional paradigms for learning. Okay, so and sort of really the thought behind outcome indistinguishability is saying what is the point of learning? What are our goals here? Okay, traditionally the goal is framed as some sort of best fit problem. Find a best fit predictor to the data. Okay, this best fit is determined by some overall performance averaged over the population as a whole. Anything else, like fairness, is viewed as a constraint that might limit your accuracy. Multicalibration, on the other hand, sort of did away with thinking about loss minimization, did away with thinking about fitting the function as a whole, and only stated this fairness condition as its first order rule. And the question is, can we generalize this approach? Okay. What we're going to do is sort of put on our cryptographer hats, put on our pseudo-random hats, and appeal to this idea of computational indistinguishability here. Okay. Indistinguishability formalizes the idea that two objects can be meaningfully different, but look the same to bounded and efficient distinguishers. Okay. So with this sort of framing and headspace, I can describe to you the high-level idea of outcome indistinguishability. Okay. Outcome indistinguishability is best described by the following game. Okay. So in this game, I'm going to present to you a triple, an X, P tilde of X, and a Y. Okay. An individual, a prediction, and an outcome Y. Okay. In addition to this, I'm going to promise you that the outcome is sampled from one of two worlds. In the first world, we're going to sample our outcome according to nature. I'll denote this as Y star being sampled from P star of X, sort of sampled from the true outcome distribution conditioned on X. In the second world, I'm going to sample the outcome according to my predictive model, okay? According to this probability that I've already presented to you, right? Okay. Now comes your job. Your job is to guess which world we're in. Okay. To guess whether the outcomes were sampled according to nature or according to the model of nature. Intuitively, we say that a predictor P tilde is outcome indistinguishable if you can't win this game. Okay. If you can't distinguish whether the outcome was sampled according to nature or the model of nature. Okay, that's the highest level idea. And we can formalize this. In fact, we're not just going to rely on the esteemed audience here today to do our distinguishing. We're going to appeal to distinguisher algorithms. Okay, these algorithms, which I'll denote D or A, sorry for the interchange, but they take in also an individual X, a prediction P tilde X, and an outcome Y. And intuitively, their output aims to guess whether the outcome was sampled from nature or the model of nature. Okay. And again, rather than just using a single distinguisher algorithm, we're going to use a collection of distinguisher algorithms. Okay, so this gives us a formal definition. So for a collection now of distinguisher algorithms of the form that I just had on the last page, we say that a predictor P tilde is A outcome indistinguishable if its behavior on each algorithm in this class, for every D in this collection A, the behavior on nature's distribution and the model of nature is similar. Okay. Here, when I'm taking an expectation or a probability over nature versus the model, the probability here is taken over X and Y. Okay. X marginally from the true distribution on individuals X, and Y then is what changes, conditionally sampling Y either from nature's true distribution or from our model. Any questions on this definition before I complicate it further? Yes.
So it doesn't depend on what distribution nature uses.
So good. So it does depend on the underlying nature distribution. Here, nature would be D star, the fixed unknown distribution that we've been working with before. Okay, so that's correct. The predictor is outcome indistinguishable with respect to this distinguisher class on a distribution, P star, on a distribution of XY pairs. Yes.
So P tilde of X are just representing a number.
P tilde of X can represent, yeah, is a representation of a probability. Good. So I'm also going to, for notational convenience, and just sort of, point is, we've been hinting at this, we can take sort of these discrete distinguishers. We can also take real valued distinguishers, allow a more general model where we take expectations now over the distribution of nature and the model of nature, as long as these distinguishers have bounded range. Okay. And so then finally, we're going to need to be a bit more precise about this approximation. And again, we'll just take the absolute difference between the expectation in nature and the model of nature, and think of this epsilon as being a small constant. Okay, so this is our final definition of A epsilon outcome indistinguishability. Okay, and so sort of like in the world of multicalibration, I want to emphasize that the collection of distinguishers we use here, this collection A, really determines the outcome indistinguishability guarantee. If I take A to be sort of very weak, simple distinguishers, then the guarantee will be considerably weak. But the hope is that if I design this class of distinguishers appropriately, then I can get out strong guarantees from the distinguishers, from outcome indistinguishability. Okay, and so for kind of the remainder of this portion of the talk, I'm going to start to go through outcome indistinguishability, go through and try to map out some of the things that we can get from outcome indistinguishability by choosing our distinguisher class correctly. Okay, the first thing to think about whenever you introduce a new model of is to compare it to the old model. Okay, so we're introducing this outcome indistinguishability as a framework for learning. We should compare to the sort of standard model for learning. Okay, I'm going to formalize this through the idea of loss minimization. Okay, loss minimization really is the central paradigm for learning, a best fit predictor, where in this problem we're given a loss function and a hypothesis class H, and a loss minimizer is any predictor that achieves loss commensurate with the smallest loss achievable within this class H. And so the question that we should ask then is, how does outcome indistinguishability relate to loss minimization? Okay. There's going to be a whole talk on this in the afternoon, but I want to just sort of give you a preview of the types of results we can show there. Okay. And that is to say that outcome indistinguishability is capable of guaranteeing loss minimization. Okay. For any hypothesis class H, I can design a distinguisher class that I'll call A sub H, where if you achieve A sub H outcome indistinguishability, then your predictor minimizes the squared loss over this hypothesis class H. This is an instantiation of a family of theorems of this form, but let's look at what these distinguishers are doing. Okay, again, I define. I'm going to take one distinguisher for each hypothesis. Okay, and what's the distinguisher going to do? It's given an X, it's given a prediction on X, and it's given a Y. And what it's going to do is compare the difference in the squared error of Y and the hypothesis and Y and the predicted value. Okay. That's what our distinguishers are going to do. They're going to evaluate the losses over the hypotheses in H and over our predictions. And what should you observe here? The observation is that these distinguishers are, make sure I get it right, are non-negative, only if P tilde is a minimizer. Computing the difference. So if these distinguishers are are non-negative, then p tilde is in fact a minimizer. Okay, so how's the argument going to go? The proof idea, and we'll see this kind of proof come up a number of times, is an indistinguishability argument. Okay, we're going to try to switch our perspective from a world. We want to reason about the real world. We want to reason about nature, but we're going to leverage indistinguishability to switch our perspective to a world where our outcomes are sampled according to our model, right? And if we can do that, then we have our model in hand and we can reason about the properties of that much more explicitly, okay? But again, okay, so the point is that if we achieve this indistinguishability, then the loss on y star, the nature's outcomes and our modeled outcomes must be similar. That's sort of what indistinguishability says. And further then, we're going to argue that when y tilde is sampled according to a Bernoulli of p tilde is the minimizer. This just follows from, you can prove it in a number of ways. Okay, so here's like the 3-line proof. So what are we going to do? We're going to look at this, the true loss of h and the true loss of p tilde for some h in our class. This difference is equal to this distinguisher value. That's how we defined it. Okay, by outcome indistinguishability, then we can switch from nature's world to modeled world. Right? That's what outcome indistinguishability says. We can switch where our outcomes are sampled from nature to a world where outcomes are sampled according to the model of nature. And then we can write, again, just by the definition, we can expand this. And by the optimality of p tilde, we know that this is the minimizer in the modeled world. Okay, so this value has to be non-negative. Okay, just rearranging then, we see that our squared error cannot be greater than any h in the class. Yeah, Russell.
So p tilde generally won't be in the class. So couldn't the squared error also be much smaller, or are you arguing that it's about the same?
That's a great question. We're not requiring the error to be the same anywhere, right? You might think of trying to equalize the error, the losses. We're not doing that here. So indeed, the squared error of p tilde might be considerably less than the functions in your hypothesis class.
I think this is the same question, but so you're saying there's no plus epsilon there? That's
no, plus epsilon is
okay.
Plus
Because
epsilon.
you're losing epsilons with the
I'm lying in terms of the approximation.
okay.
Yeah. So it's plus O of epsilon, let's say. Good. Okay, so what this says is that at least on the face of it, outcome indistinguishability is capable of achieving this kind of loss minimization. And come to Parikshit's talk for the full story. Okay. The next thing to think about is sort of, I said that outcome indistinguishability was meant to generalize or try to capture ideas from the multi-group fairness world, right? From multi-calibration. And so the question that we're going to ask is, how does outcome indistinguishability, this notion of pseudo-randomness in learning, how does this outcome indistinguishability notion compare to our multi-group fairness notion? How does it compare to multi-calibration? Okay. The sort of upshot is that outcome indistinguishability and multi-calibration are computationally equivalent. Okay. That's to say that really this outcome indistinguishability, this world where we're sort of guessing which world we're in, is multi-calibration in disguise. And the way we show this is we give explicit reductions from C multi-calibration, from achieving C multi-calibration to some notion of outcome indistinguishability, and vice versa. Okay, and really the translations, once you see them, are very straightforward, and I'll go through some of them next. Any questions on this before I go further? Okay, so the flavor of the result that I'm going to show or claim is that for any collection C, if we want to achieve C multicalibration, then instead I can enforce a certain kind of outcome indistinguishability, okay? Over this class of distinguishers that I call A sub C, which are defined as follows. I'm gonna have one distinguisher for every C in my class and for every V in an appropriate discretization of my prediction intervals. Okay, what is this distinguisher going to do? Well, it's going to evaluate C of X, evaluate whether the prediction is in the appropriate range, and then multiply by Y. In effect, what this distinguisher is doing is it's running some sort of calibration test over the subpopulations defined by C. So that's sort of the claim. The proof, again, is a very straightforward application of indistinguishability. Okay, so again, we have for each C and each V, we have a distinguisher. And we'll write out explicitly this quantity here. This, by definition, by construction, is equal to our distinguisher. What does that mean we're going to do on the next line? Yeah, switch worlds, right? Approximately equal to the world in which the outcomes are sampled according to the model. Okay, really, it's not a trick. It's not, there's no tricks here. Okay, and then from this, we can expand out in terms of this world that we understand, in terms of this modeled world, where now we can write out by iterated expectations, this quantity that, C of X times indicator times P tilde of X, and relate this back. What does that mean? It means that the difference here, subtracting out, there's some probabilities that we need to deal with. There's some alphas that we need to deal with, converting alphas to epsilons. But really, truly, if you get epsilon or AC epsilon OI, you're going to get C alpha multicalibration for some appropriate alpha. Is that clear? Yeah.
Okay, just to be clear, you're missing a second epsilon, second E expectation on the last slide. That's just a typo, right? When you said iterated expectation, there's only one. Yeah. Just to be clear, just so I'm not.
I think that what I mean by here is I'm pushing.
Yeah, so there should just be one more expectation on the next line.
Yeah. I'm just pushing the expectation over Y into here and saying that the expectation of Y tilde is equal to P tilde of X. Yeah. Yes.
So it feels like what you're saying is that traditionally you would fix one statistical test run on the hypothesis, and so now with outcome indistinguishability, what you're saying is that there's a whole class of unnamed statistical tests that would pass that your hypothesis would pass. Is it more complicated than that, or?
I guess what I'm saying is that by taking this perspective of indistinguishability, of defining a bunch of tests, defining a bunch of distinguishers, and trying to fool them, you can get interesting properties. You can get loss minimization. You can get multicalibration, and you can even throw these distinguishers in together, get something that satisfies both. And so that this may be a more expressive form of learning than just as you said, fixing one standard objective. Good. And I'm not going to go through it, but the other direction is a bit more technical, but really is just it's mechanical. It's technical, but it's not difficult. Okay, where for any class of distinguisher algorithms, A, I can define a collection of subpopulations, C sub A, such that enforcing multicalibration over this collection of subpopulations implies outcome indistinguishability. Okay. Intuitively, what are we going to do? I mean, technically, what are we going to do? We're going to define a subpopulation for each distinguisher, for each level set, and now for each bit of 0 or 1 that y could take. Okay, and the subpopulations that we're going to think about are sort of the pre-image of these distinguishers. Are sort of saying, look at the x's on which d of x v b equals 1. And where b could be 0 or 1. And so we basically need 2 distinguishers per, or 2 subpopulations per distinguisher and level set. Okay. Point is that these calibration tests over the subpopulations actually in turn implement this indistinguishability. Okay. What I want to hint at here, I don't have time to really get into it, but what I want to hint at is the fact that the degree of access that we allow to this predictor really matters. Mati, did you have a?
Yeah, so I mean, you went and when you're doing these 2 equivalences, you try to expand it. You find the class. Can you actually? I mean, is this like if I go back and forth? I mean, does that reach this clear point? Or in other words, can you actually say that multi-calibration for some classes is equivalent to output distinguishability for some class?
Yeah, so good. The question is basically like, it's a computational equivalence. It's giving a reduction from one to the other.
Right.
When, if we run this reduction over and over again, will we converge, or will we just build up more and more complex distinguishers or subpopulations? You converge after maybe 2 to 4.
So we can say that for any, you can always like just slightly expand the class and then reach something which is equivalent to something on the other side.
That's correct. Where it will get a little bit hazy or tricky is what exactly happens to your approximation factor. Like when I get C alpha, if I want C alpha multi-calibration, then I actually need to take A epsilon outcome indistinguishability with epsilon equal to say like alpha over 4.
Okay,
so I lose something in my approximation with every iteration, but modulo like.
But the classes don't become more complex.
The classes don't become more complex. That's right. That's right. Good question. Okay, good. So the thing that to emphasize here is that the degree of access to our predictive model matters. Okay, in sort of how I defined it originally, all the way back, I just said that our distinguishers get access to x, p tilde of x, and y. End of story. But really, the way that we access p tilde matters. Okay, and sort of there is a design space to design distinguishers that use p tilde sparingly or use it more efficiently. I know that's a bit vague, but the thing that I'll claim that is less vague is suppose I don't give you p tilde, I don't allow you access to p tilde. Then, in fact, rather than being equivalent to multi-calibration, these tests are equivalent to multi-accuracy, okay, to this weaker version of multi-calibration that doesn't require calibration over subpopulations, only requires unbiasedness. Okay, I also didn't go through the algorithms or the sample complexity for multi-accuracy in this talk. But the truth is that in both settings, or along basically every measure, multi-accuracy is more efficient than multi-calibration. Not significantly, not if we're only caring about polynomial factors, but like it's more efficient. It has to do with the adaptivity. Multi-accuracy is not allowed to condition on your current predictions. Doing this really makes things less efficient. And so intuitively, and it's borne out in the equivalence, not allowing yourself to look at your current predictions gives you a more efficient but weaker notion of outcome indistinguishability. In the other direction, allowing yourself access, even more access to your predictive model is also an interesting study. What we show in this original paper is that actually you can define a whole hierarchy of notions of outcome indistinguishability. If you allow yourself, say, oracle access to this predictor, then you get a concept that in a sense I can make formal is provably stronger than multi-calibration. That it requires, whereas we said that the circuit complexity of the multi-calibrated models scale polynomially in 1/alpha. If you allow oracle access, the models that you get actually, the complexity scales with an exponential factor in and that is necessary under some fine-grained assumptions. Okay, so this is the state of affairs. Again, the point is that by this equivalence, we can use the multi-calibration algorithm to learn outcome indistinguishable models. You can sort of go through exactly the same format and rederive an algorithm just for outcome indistinguishability. It works, but in a sense, the point is that just off the shelf, by this computational equivalence, you can get a learning algorithm to learn outcome indistinguishable models simply from multi-calibration. Yeah.
Some of this will be in the next talk, but for loss minimization here, it really is loss minimization for squared error, and for other losses, it's not known.
It's quite known. Yeah. Yeah.
For 0, 1.
For 0, yeah. So it's a good question. You should, over lunch, you should give yourself a homework assignment to work out whether you can get it for 0, 1 from the format I presented to you, and Google may help you.
Okay.
Yeah. Archive may help you, or you can wait till 2 p.m.
That won't help.
Okay, good. So great. So the final thing I want to talk about in terms of outcome indistinguishability is this idea of universal adaptability. Okay, so this is yet another property that you might think about that I don't know how to achieve other than through the OI or multi-calibration framework. Okay, what we thought about in this work is to sort of start with the premise that often we have a very large, rich, well-collected data set, but it's from a specific place. It's from a specific source of data. And we want to transfer insights or apply insights from this data set across different populations that may differ in composition than the source data. Okay, and so sort of the classic way to handle this is through a technique called propensity reweighting, where you sort of say, look, I have my source data. I know something about what my target looks like. I'm going to reweight my source data to look more like my target data and run estimation in this reweighted population. Okay. What if we don't know the targets up front? What if we don't, what if we want to handle a bunch of different targets? Is there some sort of way that we could learn a universal format for a predictor or for an estimator that would give us valid estimates in these downstream target populations? Okay, and what we show is that whether you call it outcome indistinguishability or multi-calibration, for any that outcome indistinguishability is capable of guaranteeing this universal adaptability. Okay, I'm not going to write the formal definition of universal adaptability right now. Maybe we'll see it in Christoph's talk. I'm not sure. But basically what it says is that this predictor, this imputation estimate using this predictor P tilde will be competitive with the target specific propensity reweighted estimate. If you understood what that means, great. If not, no worries. Basically, it gives you some sort of shift robustness. And it says for any collection of propensity scores, for any collection of shifts, you can achieve this notion of universal adaptability. And again, sort of the point is that this collection of distinguishers, what's it going to do? It sort of says, for every shift that I would want to anticipate, or that I would want to handle, anticipate it. Compute what the propensity reweighting would be, and be indistinguishable even when I run this. Even under that propensity importance weight shift. And once you do that, basically you get it pretty immediately. Using, again, the same exact argument that we laid out before. Okay, so yeah, we're starting to get a sense of what we can learn with outcome indistinguishability. The one thing that I wanted to say about our results here is that a certain meta approach for learning predictors with formal properties is emerging from a number of different works, where the learning algorithm goes as follows. First, you identify your favorite property. Okay, maybe that's your 0th order step. You find some property that you like. Okay, then the next step is to prove that nature's model satisfies this property. Come up with some proof that nature, that if you could learn the Bayes optimal predictor, then you would satisfy the property. Okay, from that proof now, devise a set of distinguishers. Okay, mine that proof, look at what you need for that proof to go through, and come up with a set of tests that if you fooled them, your proof would still go through. Okay? And then once you have this class of tests, this distinguisher class, just learn an outcome indistinguishable model with respect to that distinguisher class. Okay. And sort of immediately, if the proof can't distinguish between P tilde and P star, then P tilde must satisfy the property. And sort of, if you look at a lot of the results on outcome indistinguishability, you can recast what's happening there as an instance of this meta approach. Okay, so I think this is really kind of an exciting opportunity for you to plug in your favorite property here. Like come up with new properties that you might want to learn and try to just turn the crank here. Yeah, hopefully that's clear. So I want to wrap up, and I'll just finish with talking about 2 directions for future research that I think are particularly interesting in the vein of multicalibration and outcome indistinguishability. Okay, so for multicalibration, one thing that basically all of these, I don't want to say all, a lot of these fairness notions, including multicalibration, they work in the world of sort of supervised learning, a fixed individual outcome distribution. But often the predictions we make actually have consequences in the real world, right? If I'm using a prediction, if I get a prediction that says I'm high risk for heart disease, my doctor is likely going to tell me to do something, take medicine, go exercise, and intervene in a way that may actually change my risk for heart disease. Okay, that's a way in which these predictions actually can influence the outcomes that we're observing. Okay, this framework was formalized by many of the people who were in the audience on the so-called performative prediction setting. The predictions we make can influence the distribution on outcomes that we observe. So I think a really interesting open direction is to try to formalize what it would mean to develop multi-calibration like fairness notions in a world where our predictions have consequences, in a world where we need to reason not just about sort of what our predictions say, but what outcomes they induce. Okay, we have some very initial work towards this direction, at least towards understanding accuracy in this setting, but fairness is wide open. I think there's a lot of technical and conceptual work to be done there. Okay, and finally, the open direction with respect to outcome indistinguishability is really along these meta approach lines, right? We saw that outcome indistinguishability gives you multi-calibration, loss minimization, universal adaptability. Really, the question is what else, okay? And a lot of these works sort of, we're building up this compendium of things we can get from outcome indistinguishability. It's maybe a good way to write a lot of papers, but an inefficient way to understand something. I think the real question here is there some unified guiding theory that akin to VC theory or akin to proof, sum of squares proof complexity that tells you, look, here is a property that I've come up with. Write down this property in some formal system, and now immediately turn the crank, and out from this crank would spit out time complexity, representation complexity, and sample complexity needed to learn a predictor with this property via outcome indistinguishability. I think that's it's a lofty goal, but I don't think we're so far away from this. So I'll pause there and happy to take any questions. Not that you're bothered by this.
No, I'm just curious. So, for the computational aspect, for the last question,
yeah,
the computation aspect is a very hard question, of course. From a statistical perspective, why isn't VC the answer also here? Because VC is necessary and sufficient for.
That's right.
What answer are you looking for that's not VC? Presumably there's dependence of the exponent in alpha, but that's
no. So this is right. You're correct. The answer I'm looking for is maybe one step removed, right? So VC of the distinguisher class, yes. But the question is like, I write down an analytical property of a predictor that I want. Some property. How do I translate that efficiently into a distinguisher class that would guarantee me this property via outcome distinguisher? And so, for instance, something akin to sum of squares. Can I write this in a low degree polynomial proof system that would tell me that actually I only need distinguishers of, degree K polynomials? Yeah, it's speculative. I don't know exactly what these things mean, but I think there's something to be done.
I wasn't fast enough to look up some of the papers that you mentioned, and it might be in there, but I was wondering if for the auditing, you have settings where you take into account the data sparseness, in particular for some of the subgroups, and the inevitable higher uncertainty that you have in this auditing.
This is a great question. So the question is about sort of sparseness or density of the populations that we're trying to audit or trying to understand. And everything that I've said in this talk assumes that you have data about the populations that you care about, and that you have enough data that you can get valid estimates in these populations. Undoubtedly, though, even if you have as much data as you want, if you have less from one group than another, then you have higher uncertainty in this group. And so I think is one direction in terms of not one direction, not necessarily thinking about feedback loops, but thinking about how do we operationalize fairness would be to somehow reason about the uncertainty in your predictions, in addition to the predictions.
Yeah, in calibration, oftentimes as you, instead of having two groups, have 3 or 4 groups, you get sort of an exponential dimension.
Yeah.
But I don't see that sort of showing up in the outcome indistinguishability. So is that, have you thought about more than one category where you have dimensionality problems?
I see conditioning.
Yeah, if you condition on a little epsilon ball in 5 dimensions, well, it's epsilon to the 5th.
Yeah,
Six
yeah, yeah.
dimensions, epsilon to 6.
Good. So we do. So we do have a version of outcome indistinguishability that can generate non-binary. Right. So this is the type of conditioning problem. Just more general distributions. If your specification of what it means to have a certain prediction is multidimensional, then now naturally you're going to have an exponential blow up in that. It does show up, and I think we have some. That's a good question. I need to think about it for a moment. In some models, we give algorithms, but I think they all depend linearly on, say, the support size of the distribution, and in terms of the problem, sort of the place this exponential dependence is going to show up is in the sample complexity, is in partitioning the universe according to the different predictions. I think that's a good question. Is that true? Did I say something wrong?
I think you should ask Dean the question back and say, how do you define calibration in k dimensions in ways that doesn't involve this exponential growth? Right? Because as you say, when you condition, you're going to have 1 over epsilon per k vectors. So the starting point is what's your notion of calibration, and maybe that will map weaker notions of calibration might map to weaker notions of indistinguishability.
Yeah. Good.
So going back to your next slide, unified data. One question is like, like you said, one answer is fix a proof system, write in that proof system, write a proof of why P star satisfies whatever property, and set of distinguishers of like whatever functions that come up in the proof. So you're looking for a more satisfactory answer than this, right? So do you have a guess for what like answer, like, because this is an answer?
Yeah, I don't. It might be the answer. I don't know. I haven't given it much thought beyond that. But I think it's an interesting question. Great. Thanks so much. Thanks for the great questions. We'll meet back here at 2 p.m. for Virtual Talk, where you can learn all about